and the likes. So without further ado.
Thank you very much, Brian. So, hello everyone. Phil Kilby from Data 61 in Australia. And pardon me, I'm still recovering from jet lag. I've had about 8 hours sleep in the last 3 days. And so do pardon me if I trip over words and stuff. Okay, so we're going to be looking at the vehicle routing problem with time windows. And we'll start off with just defining exactly what that means and then a few different ways of solving it. And I guess right from the outset, I've got kind of two goals here. One is that, actually three. The VRP in itself is a very interesting problem, at least I think so. That's why I've been studying it for a very, very long time. It's also a really good example of a classic combinatorial optimization problem. And a lot of the techniques that I give you here, you can just pick up and apply to a whole bunch of combinatorial optimization problems, which makes them pretty cool. And the third thing is to just introduce you, if you have not seen it before, to a bit of constraint programming. It's another nice, neat little toolbox that you can apply to a bunch of problems. Okay, so what is the vehicle routing problem? So the classic statement is you give me a set of customers, each of whom needs some sort of service, or a visit to deliver some goods, or a maintenance scheduler who has to repair your lifts or whatever. Bunch of customers that require a service, and a fleet of trucks that is going to move them around to provide that service. You give that to me, I'll give you back an assignment of customers to vehicles and the route that vehicle is going to drive around the customers to minimise the total cost of that. And in the classic statement, it's just the total distance travelled. So this is a classic solution from one of the benchmark sets that we use in VRP. This is what it looks like in real life. So this is an actual solution. We were solving a problem, 7,000 customers in Sydney, Australia, getting daily deliveries of bread to all of the supermarkets and corner stores around Sydney. And you can see that they're quite a complicated set of routes. Okay, it's based on the travelling salesman problem that you probably have come across. You get a bunch of cities, and you know the cost of travelling between each pair of cities. What order do I visit all of those cities in to minimise my cost? On the right there is one of the largest TSPs solved exactly. It's every city, town and village in Sweden, 64,000 of them. And it took a mere 88 CPU years to calculate that exact tour. Okay, and you can see that once I've made an assignment of customers to vehicles, I'm solving a TSP in each of those vehicles. So why do we study the VRP? Yeah, first of all, it's hard, and because it's hard, it makes it kind of interesting and fun. But it's also really useful. As it says there, in Australia, it's a big chunk of the economic activities actually getting things around the country. And just in case, for those who don't know about Australia, this is the other reason why we're really keen on getting our transport right. Australia is really big. It's actually bigger than the continental, only slightly smaller than the continental United States. And it's actually much bigger than all of Europe. So getting the transport stuff right is important. In the context of robotics, it often comes up as a sub-problem when you're solving some of the allocation problems. So Brian was talking about an example on Tuesday where you've got two submarines that are moving around doing different tasks. And so in that case, the tasks were assigned to each of the submarines. But you can imagine if they had a couple of the gliders and a couple of the ROVs, then assigning which tasks each of those vehicles were to do, you'd be solving a travelling salesman problem there. And the problems get more and more complex, the more and more tasks and vehicles you have available. Similarly, I think we had... an example of assigning, what are they called? The planes that put out fires to various tasks. Okay. So let's get into a definition of the problem. So for each of our customers, we are given the quantity that each of them requires and the cost of travelling between each pair of customers. For each of the vehicles, we know the total capacity of the vehicle and the number of vehicles that we have. And so we want to work out which vehicle serves each customer and which order to minimise cost. So the objective function here in classic academic problems, the first thing they do is try and minimise the number of trucks quite reasonably and then minimise the total distance. In reality, very often the people you're working with have already bought their fleet of trucks. So you actually know that there are this many trucks that I have to use, and what you're trying to minimise is a combination of time and distance. Time because you have to pay people by the time, distance because that's what the petrol and the maintenance cost is going to be related to. And on top of that basic objective, you often have a bunch of penalties, preferences. Pretty routes is a classic one. If I actually gave that messy set of routes that you saw in the first, the second slide, to a fleet manager, and the first thing he said is, those routes are too ugly. I can't run those routes. You have to give me pretty routes. And pretty routes meant that they had to be compact and roundish and not overlap. And we went away and resolved the problem and made pretty routes and said, that set of routes is going to cost you $1 million a year more to run than the set that I first gave you. And he said, perfect. Let's do that. So pretty routes are, but that's one. Things like soft constraints, so your capacity constraint. I'd prefer to only have 60 pallets on this truck, but I can squeeze in 64 if you really make me. And so things like that come in as soft constraints with a penalty. Okay, so the topic of this is vehicle routing with time windows, and so that's where this comes in. So what all that means is that the customer has a window of time where they'll accept delivery. 9 till, only morning deliveries or only afternoon deliveries. And so once you've got that, then you need to know, as well as the distance, the time between each pair of customers, the duration of the visit as well. And it makes the problem harder to visualise and harder for a human to solve. So this is, once again, a classic benchmark problem. Now, if you don't have time windows, you can find a really nice, pretty set of routes like that. But as soon as you put the time windows of the original problem in, you get a very unpretty solution like that. And it's also a solution that a human would find it really, really hard to come up with if they're just running around, with a pencil on a piece of paper. And so that's one of the reasons why you can often, using the methods that I'll describe today, save 10 or 20% of a company's logistics costs by using automatic methods rather than manual ones. Another version that comes up pretty often is called the pick-up and delivery problem. Think of FedEx. So I'm driving to one spot, picking up a package and then driving it to another, probably stopping off and picking up other packages and delivering them along the way. So that instead of just taking all of my stuff from the depot and delivering it, as in the load profile on the left, the load profile is going up and down. You're still not allowed to exceed the capacity at any stage. You have, And there's a bunch of other variants. Because it's a practical problem and because people do deliveries in lots of different ways, there's all of these different variants of the problem. All the ones I'm going to talk about now, you'll be able to solve using very similar methods, but just different objective functions. So the so-called profitable tour problem, where you don't actually have to visit every customer. You get to choose which ones you're going to visit, and you're going to do that on the basis of the profitability. So the total value of all the customers I visit, less the cost of actually visiting them, is the solution I'm after. And the orienteering problem is just simply maximise the revenue that I can collect in a given amount of time. Okay, so there's some ones that you'll meet pretty often in the literature. As soon as you get into the real world, it gets even richer. So in fact, there's a thing now called rich vehicle routing, where you've got things like multiple time windows. I'll accept delivery between 9 and 11 and 1 and 3. Multiple commodities. So I've got a truck that can take either chilled or ambient goods, and each of those has a different capacity, and maybe even a combined capacity. I can maybe put some ambient stuff in the chilled container if I'm desperate. Multiple depots. So I've got trucks. I might have 2 or 3 depots in my city, and so working out which depot to use to serve a customer becomes a part of the problem. Different types of vehicles running out of those different depots, and compatibility constraints. So this is the kind of thing that says I don't want to take petrol and food on the same truck, or if I have picked up this person in this vehicle, their mate has to travel in the same vehicle as well. This customer, this truck can't visit this customer if they can't fit under the eaves, for instance. The truck is too big, or this customer must visit, or this vehicle must visit this customer. The first time we came across this customer must visit, this vehicle must visit this customer was an affair constraint. The truck driver was having an affair with one of the secretaries of a particular customer, and so they very obligingly sent that vehicle to that customer every day, and we had to be able to duplicate that behaviour. Thanks. Okay. And then there are, so up until now I've assumed that we know everything exactly, but there are stochastic versions of the problem too. And where there's uncertainty, and the uncertainty can pop up all over the place, but the 3 most common ones are load. So sometimes I don't know what load I will require until I get there. So think of I was about to say petrol station, you know them as gas stations, where the truck arrives, and it's only when they pull up the lid that they work out exactly how much petrol is going to be required at this place. Travel time, this is an obvious one where depending on the level of congestion, the amount of time I take to get around can change. And existence, so perhaps on some days some of the customers actually don't need a delivery, and so you can skip over them. So you can handle this stochasticity in different ways. One of the most common ways is just to have multiple scenarios, where the scenarios are meant to represent the degree of variability that you might see. And then the simplest way of using those is that every single solution that you produce, you run across all of the scenarios and make sure that they still obey all of the constraints, and you work out the objective based on the objective value across all of those different scenarios. But there's other kind of perhaps more interesting ways. If you've actually got the probabilities, if you've been able to, if you've got enough data to actually come up with a PDF for the load constraint, for instance, then you can do something like chance constraints that say that the probability of exceeding the capacity is less than some given probability, and you can design your routes around that probability. And another development is risk-aware routing, where we might say, okay, I've got 5% risk that something will fail on this route, and I can allocate that risk in different ways. So it could be that the probability of a load excess is quite small. So if I distribute my load a bit better, I can save a lot of distance. And so I might allocate a lot of that risk into the load part of the PDF, and then just take a 1% risk on meeting time windows. Okay, and so as I said in the beginning, VRP is just an instance of these combinatorial optimization problems, and there's a bunch that you might come across in your work in robotics. Scheduling is an obvious one. Assignment, where I've got a bunch of things and I want to assign them to a bunch of other people. Husbands to wives is a classic one. And bin packing. In the bin packing problem, I've got a knapsack of a known size and a bunch of items of different weights and value, and I want to pack the maximum value into my backpack. It's an NP-hard problem, but one that can be approached using the techniques that I'll talk about today. Okay, so how do we go about solving this problem? So a few different ways. There's exact, and we can use ILP here. Constraint programming I'll get into. And then there's a bunch of heuristic methods where you construct an initial solution and then improve it using local search and meta heuristics. Okay, so the reason why we need to turn to heuristic methods is that the exact methods are really limited in the size at the moment that they can solve. So 100 and 150, the classic VRP with time windows, it's really hard to solve anything bigger than, say, 150 problems. And as you saw, the kinds of size that you need to solve are up around the thousands potentially. So let's have a look at the ways that you can model this in ILP. We do. Okay, so let's define our decision variables here, the xijk, which says that I've got this vehicle k and it's travelling directly from I to j. So if it travels directly from I to j, it gets the value 1. If it doesn't, it gets the value 0. So you can see in the objective here, the sum over k of xijk tells me, does any vehicle travel from I to j? If it does, I pick up the cost of travelling from I to j. So my objective is simply the sum of the distance of the arcs that I use. And now I've got a constraint that says for each j that isn't the depot, the sum of all of the vehicles coming in and all of the customers coming into that node is exactly 1. So there's exactly 1 arc coming into j, and there's exactly 1 arc going out of j. Sorry, out of I in this case. And then we make sure that it's exactly the same vehicle that's coming in and into and out of each of the nodes. And then the capacity constraint. So the sum over j here says that there is a vehicle, for this particular vehicle k, there is, it leaves node I. And so if it leaves node I, I'll make sure that I can fit node I's load onto the vehicle. And then there's this thing, this all would work, that's all good. Where it falls apart is these subtour elimination constraints. And so what's a subtour? It's one of these. So here we have a depot and a tour here, and then this distinct tour up here. Now, obviously, that doesn't work. But this solution here satisfies this set of equations. And so you need to introduce this set of equations, which basically says that if I've got 3 nodes, or any set of 3 nodes that doesn't include the depot, I can only have 2 arcs in the solution. So if I force it to remove one of those arcs, I get a solution perhaps like that, that's now a legal solution. And so typically if you're solving in an ILP fashion, there's an exponential number of these subtour elimination constraints. So typically you would do it in a lazy fashion. You solve it, you discover there's a subtour, you add in a constraint that makes sure you can't come up with that subtour again. Okay, so why would you do this? You can find the optimal solution. And sometimes it's nice to find the optimal solution. In line haul operations, these guys are spending $100 million a year. And so a 1% increase or decrease in their cost is worth their while chasing. The disadvantage, you can only do it for small problems. And this is, you'll hear me say this about 16,000 times a day, but one extra constraint and you'll go back to the drawing board. So unless you can capture all of your constraints, you spend a lot of time reformulating your problem. And S is huge. Yeah. Okay, so that's one ILP formulation based on this sort of successor model of S going from I to J. Here's a completely different way of modelling it using ILP. In this method, I've got a column here, and each row represents a customer, and each column represents a potential route. So this is a route that visits customer 1, customer 4, and customer 5. Now, I'm not saying exactly which order that is. I'm going to record that somewhere else. But I've come up with this route that visits 1, 4, and 5, and it costs 89 units to do that route. Here's another route that visits 1, 2, and that's all, and it costs 76. And so I list out, in best of all possible worlds, I'd list out every possible route along there and the cost of that route. And I've already said that, and I said that. Okay, and then I've got this really pretty easy problem, because all I want to do is, I've got xk now, and xk just says column k appears in the solution. So I want to minimize the cost of the columns that appear in the solution, and all I have to do is make sure that for each of those rows, exactly one column covers that row. And x equals 0, 1. And so it's a nice, simple problem. A really nice thing about this is that I haven't had to worry. It's somebody else's worry that the route that I used to visit 1, 4, and 5 was legal. Somebody else is worried to make sure it matches the capacity constraints and the time window constraints and that kind of stuff. So I've kind of put that set of concerns off to one side, and I end up with just this nice, relatively simple problem to solve. And so the way this typically works is I can't use every possible route. There's kind of, it's not even trillions, it's an exponential number. So I start off with a reasonable number of routes, and then I choose a nice one. And there's actually a really nice way that I won't go into today, but by using the dual variable associated with this constraint, that kind of gives you an idea of the cost of visiting each customer. I can then solve a sub-problem which lets me generate a new column that I know is going to go into the solution, and I can keep doing that, generating new columns and improving the solution. And in fact, if I can keep that up, I eventually end up with the optimal solution. Okay, so that's the other exact technique is constraint programming. We'll come back to that later. We'll jump into some heuristics. Usually it's some variant of construct and improve. So the easiest way to construct a problem is by insertion. So you just start with an empty route and you choose a customer, stick it into the route. Choose another customer, work out where to put it in and stick it in that position, and repeat until you've got where you want to go. So an example is a greedy solution. I choose the customer to insert that's going to increase the cost of the solution by the least, and then I pop it in that position. Okay, and so just to see how that works. No! Look, this, sorry, this worked at 10 o'clock last night. Okay, pardon me, I'll just be one moment. Try again. Thank you. Okay. I really don't know why I didn't. Okay, pardon me. So this is, you can't see that? So this is an insert method in operation. So this is, the first one has gone in. And now I don't know why that's not working. Sorry, one more go. Okay, so we're finding that the customer that's going to increase the cost by the least and then inserting it in that position that increases it by the least. And you can see that the route gradually grows. This is a time window constrained problem, and so you get the occasional weirdness like the loop there. Also you get things where it skips over some customers. It looks like that one should be closer. It will be because the time window constraint doesn't meet. And so you can see one at a time we add those in, and this is the route that we end up with using that method. And you can see that there's actually a couple of customers here that couldn't be feasibly inserted using that method. Okay, and order is important. So this is exactly the same problem, and it's exactly the same thing. I'm inserting the customer that in the position that increases the cost by the least. I'm just changing the order of choosing customers, and I'm just using a random order. So instead of inserting the customer that increases the cost by the least, I'm just using random customer, and that comes out, and that, and that, and that. So you can see that the order is incredibly important in this. Okay, so an advance on just using that greedy algorithm is regret, and regret's actually quite a useful general type of heuristic. The idea with regret is that if you have a look at this one here, if I wanted to insert this this customer, I can either insert, so this is the current set of routes, I can either insert him in that position in that route or that position in that route. Okay, they're both actually pretty good. This guy, if I can insert in a nice position there, or it would be a really horrible one if I was forced to insert him in that other route. And so the idea is that I will make sure that this customer gets the most preferred route. And I call the difference between those two possible solutions the regret. And so it's the difference between the cost to insert the second best route and the best route. And then you can expand that to K regret, where you look at 3 regret is 3 different routes, 4 regret is 4 routes. And then I'm going to insert the customer with the maximum regret, but I'm still going to insert them in the position that increases the cost by the least. And so how does insertion by regret go? Okay, so now you can see that we kind of jump around a bit more, and we're plucking out customers from in the middle of the route much more. These will be customers that, if their time windows mean that if they don't get into the route that's closest to them, they probably won't get into any route. And so you jump along there, and you can find this route. And you'll notice that in this route, there's no customers left over. So the regret has helped find a solution where all the customers have been able to be found. And then seeds actually make regret work even better. So with a seed, you just initialize each route with a customer that kind of gives a direction to the procedure. And so so here we've chosen, it's actually as it says there, choose the most distant customer from the depot, the most distant one from that, and then the most distant from those two, and you get that one. And now, as I'm building it up, you get a much more guided procedure till I get that, which is an even better solution than the one we had before. Okay. So the heart of a construction method like this is simply deciding which is the customer to insert next and where to insert it. And you have a data structure insert positions which records all of the legal positions, and you update that each time. Okay. So local search. So local search in this and other combinatorial optimization problems are often defined in terms of an operator. So one operator is a one move. So that's simply moving one customer into a different position on the route. So we've got a solution that we've produced by whatever method that looks like that, and a one move simply puts it into a different position in a different route, or a different position in the same route. So these are all the different positions that one customer can get put into. So we talk about a neighbourhood of a solution is all of the different solutions that I can reach using that operator, the one move operator. And local search simply explores each of the neighbourhoods. Another example of a neighbourhood is the swap 1-1, which is taking one customer from one route and swapping it with another customer from another route. Or a 2-1 swap, take 2 and 1. Now, you can actually get to particularly the 1-1 swap by an operation of 2 one moves, for instance. But the trouble is that if this route is close to its capacity limit, it could be that moving this node into this route makes that infeasible. And so I'll never be able to discover the 2 moves that bring the cost down. Okay, I can swap tails, which is I choose 2 visits and swap everything after them. And then there's a very powerful operator called the 2-op operator, which comes from TSP research, where you choose 2 arcs to delete, you replace them with the uncrossed arcs, and then you have to reverse the direction of the middle section. And that's really good at untying knots. Okay, and then there's OR-opt that takes any sequence of k nodes in a route and then tries to insert them in every other position in all of the routes, both forward and reverse. And it's really effective. And in fact, because it's cheaper than 2-opt, it can actually produce better solutions than 2-opt in a similar time. Okay, so local search is great, but the trouble is that you get to a certain point, and like in the one move, I've found my local minimum, but it's not the global minimum. So we turn to meta-heuristics that can help us get out of these local minima. One way to escape local minima is simply to define, larger and larger neighbourhoods. But an even more effective way is to actually use them in this thing called variable neighbourhood search, where you actually use all sorts of different neighbourhoods. So in classic VNS, you start off with the smallest neighbourhood and you explore that fully. And then you go on to the next largest neighbourhood and explore that fully. Next largest neighbourhood and explore that fully. If you find an improving solution, then you can go back and start again. Okay, and if you've got new constraints or new problems, then you can add tweaks of these neighbourhoods that allow you to fit into your new world. So, for instance, in the orienteering problem, you can unassign one customer and see if that reduces the cost, or even a sequence of customers. Okay, and we've got lots of meta-heuristics. Simulated annealing, taboo search, genetic, and then there was that people got really carried away with these biological analog routines. So genetic was really good, genetic worked great, and then people said, hey, where else in nature can we look? Ants. Ants work okay. Okay, in ants they leave a pheromone trail, and the pheromone trail helps you guide your local search. But then there were bees and moths and particle swarms and a whole zoo of methods. They all work on similar principles, and you're welcome to go and have a look at them, but yeah, it's kind of a bit strange. Okay, and large neighbourhood search, and we'll come back to large neighbourhood search because that one actually works. Okay, we're going to come back to it now. So LNS was first worked out in 97, and the one I'm going to talk about is from Ropke and Pissinger in 2007, and it's such a good idea. It's been invented lots of different times in different places. It's also called record-to-record search. So the basic idea is that you take your current solution and you destroy a part of it and then recreate it. So destroy part of it, you just simply remove visits from the solution and then recreate it. You use your favourite construction algorithm to stick those customers back in. And if the solution is better, you keep it, and then you repeat. Okay, so how do I destroy things? I just move to the unassigned list. And so an example would be destroying a sequence of visits. So if I've got this route, I just choose a sequence and unassign them, ready to be reassigned. The worst removal is another one, where I simply choose the worst arc and remove the customers at either end of that. Now I'm going to iterate over this, so I don't want to keep choosing exactly the same arc every time. And so I've got this neat thing where you choose the rth worst, where r is n to the power of n times a random number raised to the yth power. And if you've got y is about 6, then this is the probability of choosing it. So I've got this kind of a chance of choosing, the 20th worst or the 30th worst occasionally. So I don't always choose, the very worst. Okay, and I can dump visits from nearby routes so that there's a better chance of getting them to come back. And I can remove from related visits. And Paul Shaw defined this thing of relatedness that is partly, it looks at the cost, the closeness, how close two visits are, how close their arrival time is, and how close their load is. And if they're close in that sense, then they're more likely to be removed. And just dump visits from the smallest route. If you are trying to reduce the number of trucks, then that's one way of trying to distribute that last little last few visits from that route. And the main thing you need to work out is how many I'm going to dump, and I just use a random number up to a maximum. Seems to work well. So around 100. If you've got a problem with 1,000, then maybe 100 is a reasonable number. Okay, and then I can recreate the solution. And one way to do that is systematic search. And I can even afford to do systematic search because I've maybe only got 20 nodes that I've taken out, and that can be very effective. If I've got a CP thing, CP is really good at backtrack search, so it can look at all possible reconstructions. But the most usual way is just to use your favorite insert routine. And I've just described one of the ones, or better still, use a portfolio. Let's select amongst different ones that I can have. So minimum cost, the greedy one, the regret, 3 regret, 4 regret. And I'll just choose amongst those each time. So let's have a look at what large neighbourhood search looks like. Okay, so first thing I do is choose a bunch of, so this is actually the seeded regret solution that we had. And now I'm going to choose a bunch of visits to remove there, and I did that using the Rotke deletion method, so related visits, and these are related mostly by distance, it looks like there, and then I reinsert it. And that wasn't any better than the previous one, so I just choose a different bunch using the worst removal and reinsert that, and that one is actually better, so I keep that solution. Chuck away another bunch and reinsert, and that one's better too, so I'll keep that one. Chuck away another bunch, reinsert, that one's not quite so good. Chuck away another one, reinsert, and that is actually better. And so I can continue on doing that, and you can see that it's starting to look increasingly reasonable, and along the way you're producing some pretty silly solutions, but on the whole it's getting better until at last we produce what is actually the optimal solution. Okay, so LNS is great. I said if you keep this best solution, if you find a better solution, keep it, and so this is a graph of that happening. I can zoom in a bit, so you can see each of these blue dots is one of the test solutions that we've generated, and we start off with a pretty horrible solution, and this is really typical. You get a really quick decline until you're in this region, and then we just keep finding better and better solutions as we go along. Simulated annealing is another good one. In simulated annealing, I can accept a cost increasing solution. That helps me escape the local minima. And the probability of accepting an increasing solution is this, depends on this parameter T, which is the current temperature. The temperature decreases over time, so that the probability of accepting a high cost difference decreases over time. And so you can see this is a run with simulated annealing. We'll zoom in, and this is the best solution is still the green, and we've got this red, which is the incumbent. And you can see that we've kind of wandered off quite a way from the best possible solution, but then when we do find our way back, we're actually able to improve that best solution. Okay, and the adaptive LNS in Rotke and Pissinger is we're adapting both our creation and destroy heuristics. And so after each time I improve the solution, I reward both the insert procedure and the delete procedure that gave that. And so over time, the probabilities will change. So you can see here they all start off at the same probability at the beginning, and then very quickly it turns out that min insert is actually not performing very well, and so the probability of that decays quite quickly, whereas regret is doing very well, and so it gets chosen more and more. And similarly, the select method, the method we use to destroy the solution, looks like in this one, worst selection isn't doing so well, but just choosing randomly is. Okay, and the nice thing about this LNS in the VRP context is it can be used for a whole bunch of the different variants that I was talking about in the beginning. So VRP, time windows, pickup and delivery, and all those other rich vehicle routing variants, it can be adapted to very quickly. Okay, so we've got several successive insertion techniques, various ways to choose the next one to visit and where to insert, and we've got VNS and LNS that both perform very well on a wide variety of these routing problems. Okay, so what's wrong with that? And the basic problem is that you get a new constraint, you basically have to rewrite all your code. And often it's right in the core. I can remember having to write a duration constraint. And duration constraints, because you've got waiting time in the middle of when you've got time windows, if you arrive before your time window, you wait for a while. And so when you insert a customer, it's not exactly clear how much that's going to affect your duration. And so inserting the check for a duration constraint, instead of just being this one little spot in my code, it actually popped up in about 16 different spots in the different checks and updates. So each new constraint adds a lot of complexity to a problem. And they can interact. So multiple time windows is even harder with the duration calculation. Okay, so the alternative is to use constraint programming. So for those, how many have come across CP? Yeah, okay. So we'll just do a quick CP 101, don't we? Yes. So it offers a nice language to represent your problem. And it's simply in terms of the decision variables and the constraints on those variables. It offers systematic search and also heuristic search. So we define a variable based on their domain. It's usually a finite domain. CP certainly works best, I would say, in finite cases. So you've got x in the integer interval there, or the element of a set. And then you've got constraints that link variables. And constraints are only as good as the library that you're using. So you can have simple linear constraints like the first one. Nonlinear is fine. They propagate very well. And you've also got these things called global constraints. So those first two only used like a fixed number of variables, 3 variables in each case. The global variables, it's undetermined how many they're going to operate on, because I don't actually know when I'm defining the constraint exactly how many variables are going to be in X. But the cardinality constraint says that in the array X, the variable 1 occurs between 4 and 5 times. Or I might have an all different that says in the set X, every single variable in that array has different values. And I can define my own my own constraints in a VRP context, where I might have a constraint that says I need a half-hour break between 120 and 240 minutes into the route. Now, CP uses propagators. Each constraint will have a propagator. And what that propagator's trying to do is to make sure that each value in the domain of the variables that are mentioned in that constraint are in some way consistent. So let's have a look here. I've got the constraint x is less than y, and when I come in here, x has these values and y has these values. Now you can see that I've got this value 9 in the x domain, but in y, there's no value in y which will allow the value x to be 9. And so I can remove 9 from the domain of x. And similarly, in y, there's no value of x which will allow that constraint to be true with y equal 2. And so I can remove 2 from those domains. And so now, after the propagation, I've reduced the domains of my variables. And as soon as any of my variables are touched, then any other constraint that mentions those variables is going to wake up and they're going to propagate. And maybe, if 7 gets removed from the value of x, then this constraint is going to wake up again and remove y from the domain of, 8 from the domain of y, etc. So you get all of these constraints firing up and removing domains, removing elements of the domain. Okay, so the typical execution is that I work out, store all of the values of all of my domains. I choose a variable to instantiate, and I give it a value. As soon as I give that variable a value, all of the constraints that mention that variable are going to fire, and there's going to be a bunch of propagations happen. And I keep going around the loop until all of my variables' domains have stabilized. And then I've got 2 things have happened. Either I've found a constraint, or I've found a variable where all of the elements of that domain have disappeared. And that's called a failure. It means that the choice that I made has led to an inconsistency. And so that choice is not valid. And so I make sure that I can never make that choice again. I remove the instantiated value from the first variable's domain and go again. Or I found a new consistent solution, and then I repeat the loop, choose a new variable, choose a new value to assign to it. Okay, and yeah, I can do a systematic search and when I find a solution, I say, oh, that's interesting, record that, make sure that I can't find that solution again by removing one of the elements of that solution, and then fire up again. Okay, and so the basic element of the loop there is to choose a variable to assign and choose a value to assign it. And that's almost exactly the words that I used for root construction. And so the CP element there is, I've got the variables representing the customers and the variables representing the root, and I'm making assignments to those. Now the problem with CP is that the step to new solution does not work as well. So if I've got a VNS, variable neighbourhood search, I've just done a 1 move and changed the solution. I actually have to check. I can't do anything clever. I have to just instantiate that in the whole solution and ask CP, is that feasible? And it's just going to answer yes or no. Okay, so I said CP provides an expressive language. This is Minizinc, which we'll just have a quick look at because you'll be playing with this in the laboratory if you choose to do so. So I've got here the type and then the variables. So I've got a string, which is name, just for display purposes. And now I've got int number of customers, or num-custs. Now, later on, we'll see var visits. That means it's a variable. This doesn't have var, so this is a parameter of the problem, and I have to instantiate that at runtime with some sort of value for num-custs. And then I'm going to find this set of ints, which is customers, which is 1.num-custs. I've got the number of locations, which is the number of customers plus 1. This is, I'm assuming, 1 depot here. So I've just got an extra location for the depot, and the locations is 1 to numlocks. Similarly, I've got the number of vehicles as an input parameter, and I have 1 route per vehicle here. I also have as input the x and y coordinate of each of my locations, and an array of a 2-dimensional array of the distances. And now my decision variables. So I have a variable int, which is the objective, I have the root of, so for each visit I have the root of the visit. For each visit I have the successor, and for each visit I have a Boolean saying whether it's assigned yet or not. Now I can use this all different constraint to say success. So if you think about a TSP, every visit has to have a unique successor. So I can use the strong propagation of this all different in SUC. There's also another global constraint called circuit that makes sure that what I get is a circuit. And that propagates in a different way to all different. And so those two can actually work together. Here's my objective, which is the sum over all of the visits of the distance from the location of I to the location of the successor of I. So you can see that's a fairly complex semantics that you've got there for defining your constraints. And here's my capacity constraint, which just says that for all visits such that J is the route that they've been assigned to, sorry, I'm going to take a sum over all of those I's of the demand of I is less than, and that should have been QJ. Sorry about that. Okay. So we've got this lovely expressive language. We've got each constraint is encapsulated. Yay. So I only ever have to say, to impose my duration constraint, all I have to say is that the time I get to the last visit is less than duration. Yay. I'd never have to think about it again. And the constraints interact naturally. So I can do all of the propagations for my capacity constraint and then do my propagations for the time windows constraint, and they're going to bounce off each other. And the nice thing is that constraints guide solution. Each time I insert a visit, all the constraints fire. So for instance, I insert a visit into a route, all the constraints fire, and it'll be able to say, this visit can no longer fit in that route anymore because of the capacity constraint. And so that route will no longer be allowed for that visit. So when I next think about that visit, I don't even think about putting it into the route that's just become illegal. And so that also helps me, now that I know that I can't fit that visit in that route, I've only got one place left that I can fit that visit. And so it becomes an important one. My regret will now probably pick up the visit that only has one place left to insert. So that's what I mean by the constraints are able to guide the solution to a feasible and good solution. Disadvantage if you've got using something like Minizinc can be slow. It's expressive, and so almost always with expressive you get slower stuff. And no fine control of solving. In Minizinc you can't really control very much how it's solved, although we'll play a little bit with that. But you can go to a constraint programming library like G-code that allows much finer level. Okay, so two ways to use constraint programming. One is a rule checker. If you're using variable neighbourhood search, you're just simply using it as a rule checker. I can express my rules neatly. I do a change. Does that work? I would say the other way to use it is properly, where you're actually constructing and it's guiding the search. The trouble with VNS is, and using it as a rule checker, is that CP isn't able to return a reason why it said something is illegal. VNS says, here's a solution I've created by moving one of my visits into a route. And CP says, nope, that's infeasible. Now the reason is that breaks the capacity constraint. And it's going to break the capacity constraint regardless of where I stick it in that route. But CP can't say that. And so my variable neighbourhood search is going to say, okay, what about if I insert it after the next one in the route? No, that's illegal too. Oh, what about if I insert it in the next one? No, it's illegal too. And so you're not getting back any information. It's not helping you craft your solution. If you're using it in the construction way, it's helping you craft your solution. Okay. So how are we going here? Yeah, we've got time. So I'll go through the formulation that is represented in the laboratory for you. It's a little bit technical, but it's useful for you to understand the formulation that I've got there. That formulation you can actually use to solve real VRPs. It's also a reasonable way of, if you haven't played much with CP, it's a nice way of getting to know CP and playing around with the different possibilities there. So, a bit of vocabulary. We've got a solution made up of routes, and in this case, we're going to have one for each vehicle. Our route has a sequence of visits, and some visits serve a customer. One trick is that each route has a start visit and an end visit. Now, the nice thing about that is that now I don't have to play around with, if I'm the start visit, then I do something else. I just get to, all the visits just have a successor and a predecessor, and I can treat them identically. And I've got one additional route, which is the unassigned route. So that's where I put everybody while I'm thinking about where to insert them. Okay, I've got N customers, V vehicles. I've got M routes, which is one for each vehicle plus the unassigned. And I've got fixed locations where things happen. So I've got one for each customer and one for the depot. It's possible to put in different commodities, but in the formulation you'll see we've only got one commodity. That is, like you might have a constraint on the weight or the volume. In this case, we're just doing one. We've got the time and we've got the cost. And it's fairly important in CP for technical reasons that they obey the triangle inequality, but yeah. Sets of, we've got customers, vehicles, routes, start visits, end visits, all visits. Okay. And we use the index to reference our customers and routes. The visits, we've got the first N visits are the customer visits, then we've got the start visits, then we've got the end visits. And we've got a bunch of stuff that we know, the value, the demand, the earliest and latest time we can start the service, the capacity of the vehicles, the times and the cost of travel. And the way we're going to define our solution is using a successor variable. SI gives the direct successor. Sometimes it's advantageous to have redundant constraints. We have these redundant variables P. We probably won't bother with those. And then we've got the route variable, which route is each visit assigned to. Okay, so just to make that explicit, we've got our route 1 and route 2. We've got the start visits are 6 and 7, and the end visits are 8 and 9, and our table. So for node 1, its successor is 4, its predecessor is 2, and it's on route 2. Route 6 is a start visit, so its successor is 5. Its predecessor, it doesn't have a predecessor, and its route is 1. Okay, and we're also going to have a couple of variables, an accumulation of the quantity and an accumulation of the cost in getting to a particular visit. And for time problems, we've got an arrival time, a start time, which, as I mentioned before, can be different if I have to wait, and a departure time. Yes. So with just those variables, there's a whole bunch of different VRPs that we can model. The basic VRP, time windows, multi-depot, heterogeneous fleet, open VRP, which is one where I don't have to return to the base. Compatibility constraints are ridiculously easy, and PDP problems. The things that we can't model. Still going on stuff we can do. Yeah, variable load and unload times by changing the departure relative to the start time, and all those things you can see there. Okay, what can't we model? Dynamic problems. So problems where I'm introducing new customers. CP has this really fixed idea of a domain, and it really doesn't like you saying, oh, you know, that variable that I said had 100 elements in its domain, I want to make that 101. No, you're not. It just really doesn't like that. And another example is optional driver breaks. So I might have one where if it's, I need a break every 2 hours. So if as soon as my length of my route goes over 2 hours, I need to invent this new visit, which is a driver break, and it doesn't like that either. Yes. Okay. Our objective that we're going to use in the CP is basically I don't know why I've said I as an element of E. Anyway, it's the cost of getting from I to J, and then the value of the visits that we don't use. And if I really want to try and visit all my visit all my customers, then I'm just going to have VI really, really high, so that it makes sure that as many customers are visited as possible. So here's my constraints. I'm going to accumulate my my objectives, so that the cost of getting to the successor of I is the cost of getting to I plus the cost of getting from I to SI. And I'm going to do that for everybody that has a sensible successor. I'm going to accumulate time, so the arrival time at the successor of I is the departure time at I plus the time from I to SI. Implement my time windows, so my arrival time has to be less than the start time. The start time has to be less than the late time and greater than the early time. And this is where you get the difference. This may or may not be the same. We start all of the starts at time 0. Accumulate my load, so the quantity of at the successor of I is the quantity at I plus the demand at the successor of I. No, the demand at I, sorry. And now we put the upper bound on the quantity, and we start all our starts at 0. And if we've got a PDP, we want to make sure that we don't want to go negative at any stage. And we just have some consistency, which says that the successor of my predecessor is me, the predecessor of my successor is me, and the starts and ends all sit on their right. And the root of my successor has to be the same as the root of me. And this one says that the starts and the ends are on the right route. Okay, and so we can also have, rather than that horrible subtour elimination thing that we had to do in ILP, we've actually mostly got built-in circuit constraints in most commercial CP solvers. Now, I might just skip over the propagation. Just let it be known that these path constraints have a nice way of propagating them, including a nice way of working out a lower bound on the cost. Now, the nice thing about that is that I can stick in if I'm in the middle of a hill climbing search, for instance, and I've already found a solution with value Z, then I can put in the constraint that the value of the next solution I find has to be less than Z, so that I'm forcing it to go down. So I can be 2/3 of the way through constructing a solution and discover that my lower bound has gone above Z. Excellent. I don't have to finish constructing that solution. I can just chuck it out now and jump straight back, fail, and go on to the next iteration. Okay, so how does LNS work in the context of CP? It means that I'm going to relax some of the variable assignments. So for instance, I'm going to relax the root of and successor variables for a bunch of customers. Recreate solution, I'm going to use the insert methods, and the nice thing is that by inserting one by one, I'm getting that guidance. I'm getting the full power of CP to guide my search towards a feasible and better solution. Okay. So, and another nice thing about large neighbourhood search is that it's really versatile. So as soon as you come up with a nice construction solution that you like, you've kind of got an LNS for free, because I can, it doesn't take much smarts to delete part of my solution, and then I can use your construction method to recreate that solution. So for instance, a knapsack problem. I've got a greedy construct algorithm, which is to insert the best value item into my backpack. In an LNS situation, you might randomize that. Using that worst thing of rand to the y, just to bias your selection. Instead of doing exactly the most valuable each time, I'm just going to mix that up a bit by biasing it towards the best each time. And so now I've converted my good construction heuristic into a meta heuristic in like 2 minutes. It's funny, immediately before presenting this, I was working on a 2D packing method, and I realized I had a reasonable construct heuristic. Hey, 5 minutes later, I've got an LNS solution for my problem. Okay. And just a few extra things. So, adaptive decomposition. So even we can handle problems of quite large size. So using a Ropkin Pissinger type thing, a problem with 100 nodes you can do in a couple of seconds. A few hundred nodes you might take 5 minutes. A few thousand, you want to let that run for a couple of hours. Bigger than a few thousand, so tens of thousands, and you're going to have to start thinking about decomposition techniques. And so this is one decomposition technique. So if I've got that Sydney solution with 6,000, that had, I think there was 400 vehicles in there. So I've got a solution with 400 vehicles, but I don't always have to think about all 400. I can just choose a couple. Here's a solution with 3 vehicles, but I can just consider 2 at a time and just do LNS on the routes and customers that form that smaller part. So instead of a 7,000 problem, I've now only got a 2-vehicle, 40 customer problem to think about, and I can solve that really quickly. And then all I need to do is think about how to combine, which routes am I going to combine? And I'm going to do ones that are close together in space, close together in time. And in fact, one of the cleverer ones alternately divides it by space and time, which is what I've just said. Okay, and was also going to mention, and the slide didn't make it into this deck, about another decomposition technique. So and there's this a tactical problem. The problem you can often face is the company wants to design a set of routes that they're going to run each day for the next 6 months, and then they'll do a route review. But over those 6 months, the demand is going to be changing day to day. So we've got this stochastic technique of looking at a representative sample of the demands across those 6 months. But if I use all 500, I turn a 100, I've got 100 nodes, 100 customers that I'm visiting, but now I've got 100 data points for each of those customers, and now I've got a seriously messy 10,000 node problem to think about. And so there are ways that allow you to just think about a single day at a time, and using this technique called Bender's decomposition that hangs off one of the ILP solutions, you can use the information from each of the separate days to guide a search that basically puts a value on each of the customers and how valuable it is to have each customer in each route. That lets you solve just a series of 100 node days that eventually end up with a solution to all 100 days that's both efficient and feasible on each of the days. and stay tuned for a paper on that shortly. Okay, so that's everything I wanted to talk to you today. So what we've come out of today is a really strong heuristic technique of doing successive insertion, and then we've leveraged that into a large neighbourhood search algorithm. And that successive insertion and large neighbourhood search use of that is a technique that you can apply across a wide variety of combinatorial optimization problems. I've argued that CP is a natural for solving real-world vehicle problems. Every single time I've had to solve a real-world vehicle routing problem, every single time that the customer has said, yes, but we do things a little bit differently. And they've had an extra constraint. And rather than having to go back and rewrite my entire system and fiddle with that goddamn duration constraint again, you can just add this one extra little self-contained block of code that implements that constraint. Most of the time, LNS is able to just swallow it up and use it, and you get this this nice extension that's able to handle the new problem. And we've got CP that can do complete and complete-ish, which is you can limit the completeness of your search. And I've said that LNS is a natural for CP since it leverages the full power of that type of search. So that's it for today. Just one thing. There's one thing I wanted to show you in the tutorial. Yeah, you can see that. So this VRP.mzn is the Minizinc source file. VRP.mzp is the project. You can open that. And here's the model that I've described. The one thing that you have to do is in the configuration tab, there's just a bug in Minizinc. This user-defined behavior button needs to be highlighted. And so every time you open a project, you'll just need to do that. And then you can go back to VRP and, and run the program. Oops. And starts running the program and producing a solution. Okay, so I just wanted to point that little quirk out. So that's it for today. Thank you very much for your attention. Question? I think we've got time for a couple.
So basically, I want a quick question. Usually the constraints related to the time windows look like hard constraints.
Yes.
Like customers can only be served at this time window. Can you relax a little bit that constraint, like a soft constraint, so it's that like the customer can be visited, but you get less reward or higher cost, and it still can be modeled as a CP?
Yes. Yeah. You end up having the so you might have a 15-minute grace on each side. So your new hard constraint is your old constraint minus a half hour, minus a quarter hour, plus a quarter hour. So you're still going to hard constraint that, but then you can have an element in your objective function. And you can even do absolute differences in CP very easily. So you just say, the absolute difference between this and my intended arrival time, multiply that by your penalty. So that's certainly doable.
Thanks for the lecture. It was quite nice. So yesterday, Professor Daniel, he talked about trust in a plan.
So, just means the trust in the plan?
Yeah.
Yeah.
So I'm just curious about, you did mention that coming up with trust for anything related to constraint programming might be tough. But then over a period of time since people started looking into VRP, how did people characterize trust on any of those metrics?
Yeah, look, I think that the closest thing that you come is a concept of robustness. Under what circumstances does my solution hold? And so that's where you get into the risk-bounded or, chance-bounded or aware modelling techniques that say a lot of work is done in purely deterministic routing, but I think you do need these concepts from risk aware and risk bounded that allow you to say, this will, given the data that you've given us, the solution I'm giving you will work on 95% of days.
Accurate.
And that's more of an aspiration that a large body of work on VRP doing that currently.
Yeah, exactly. Yeah.
For using these on real world problems, how do you generally go from the abstract representation here to like a real world map?
You basically just need to know the time and distance between every pair of customers. Google will give that to you. So I just read it in a pumpkin crate matrix.
Question about performance. So if you didn't have all these new constraints, I think the customers would overstate that you have set constraints. How well does LNS and CP perform against like genetic algorithms or like ACO?
Yeah. A hand-coded meta-heuristic like that is always going to outperform CP, but probably only by a couple of factors, not an order of magnitude kind of thing. You do pay for that that flexibility. So what I would say is that if you know exactly the constraints of your problem, and you can get your customer to hold their hand over their heart and say, that will never change, go with a hand-coded solution. But if there's any chance at all, you're going to get your time back using CP.
Does it ever occur in practice that there are new locations generated dynamically? And what do you do then?
Yeah, I don't use this method because you've just done that horrible thing of introducing a new point in the middle of the solution. It becomes, you get kind of aspects of planning coming in there. So a classic example is routing with transshipment. So it could be that I've got this package and I can either take it directly to its destination, or it could be that there's a hub along the way and I can just drop it off at the hub and another vehicle that happens to be going in that direction can pick it up. As soon as you get that kind of problem, it's got an entirely different complexion to this and a whole bunch of different methods that you can use.
So, like, you have a lot of constraints up there, and I imagine that's one of your simpler problems.
Yeah.
So, are you able to reuse some of those structures or some of those sets of constraints, or do you have to rebuild all of these by hand for every problem?
See, that's the thing about CP. I've only ever defined one capacity constraint. Like that model that you saw goes straight into every model you build. I pick up the library version of the subtour elimination constraint, the set constraint that's just given to me at the time. So yeah, no, there's a lot of reasons. That's it. Good. Okay. Thank you very much.